Hello everyone, my name is Karan and I'm one of the data scientists working on the OpenShift CI analysis project. The ultimate goal of this project is to analyze continuous integration data and develop a set of AI tools to supplement and improve the CI process. So naturally, one aspect of this is to analyze the CI tests in terms of the bugs that are associated with the test failures. This would help us answer questions like, are there any particular jobs that have more bugs than others? Or are there any particular components of OpenShift that are more buggy and are blocking more of the CI pipeline? And so on and so forth. In this video, my colleagues Hema and Akanksha and I will walk you through this notebook that shows how you can access the Bugzilla data and more importantly, how you can connect it back with the test grid tests to perform further analysis on the CI process. So after some investigation, we found that the connection, the linkage between test grid and Bugzilla can be made using the search.ci.openshift website. So this website is sort of a database of CI test failures for OpenShift. So here you can type in any test name and any job name, and then simply click on search to get a list of all the bugs that are associated with this particular test and job combination. And that is exactly what we'll be doing in this notebook. So first, we'll get the dashboard names on test grid. So these are the dashboard names listed up here in the topmost row. Then we'll get the job names listed under each of the dashboards. So that is these job names in the center row. And then lastly, we'll get each of the test names under each of the jobs. So these are the test names listed on the leftmost column on here. And then once we have these three pieces of information, we will simply query the search.ci.openshift URL to get all the linked bugs for each of the job, test, and dashboard combination.
Hello everyone, I'm Hema and now I'll be going over how we can fetch all the linked and associated bugs under each test for a given dashboard. As Karan mentioned earlier, we will be querying the search.ci.openshift.org URL for fetching all the bug IDs. Here we will be looking at the Red Hat OpenShift OCP release 4.2 informing dashboard, and we will be fetching the past 14 days of data from the current timestamp. To do this, we have defined a function which takes as an argument a tuple comprising of two elements, where the first element is the shared dictionary where the final result will be stored, and the second element is another tuple comprising of the dashboard, job, and test name. We do a requests.post against this search.ci URL along with all the required parameters. We fetch the entire HTML content page and we further process it to extract only the relevant bug ID fields, and we store this into a list and append this into our resultant tuple. We then move on to find the list of arguments that need to be passed to our function, and we invoke our function with this list of arguments. Since this is a compute intensive task, we have a multi-processing step in place which will parallelize and further improve the process of fetching and querying the bug IDs from the search.ci URL. As we can see, we were able to fetch the bug ID for the above mentioned dashboard, job, and test. Now that we have this list of all the bug IDs, we want to store these results into a suitable data frame having the dashboard, job, test, and the list of bug IDs as the relevant columns. We also drop all those rows where there were no linked bugs and only retain the rows having non-empty linked bugs. And this is what the final data frame would look like. Now that we were able to fetch the bug IDs for a given dashboard and job pair, we will try to fetch the linked bugs for all tests of all test grid dashboards. We will be invoking the same function as we saw above, but this time as an argument, we will be passing all the tests found in all the test grid dashboards. Now this is again going to be a highly compute intensive task, so we have the multiprocessing step in place which will parallelize and optimize this fetching and querying process. We then get the list of all the associated bug IDs and we append this into our final resultant data frame with the relevant columns that we saw listed above. We will drop all those rows which did not have any linked bugs and retain all the non-empty fields. And we finally convert this data frame into a suitable Parquet file and have this as a dataset in our repository for further analysis.
Hello everyone, I am Akanksha Duggal and now we'll be getting the Bugzilla details. Once we get the bug IDs, we try to fetch the information associated from Bugzilla. We use the API Python Bugzilla to fetch the information associated to each bug ID. Using a sample bug ID, we will look at the various fields and will exclude the deprecated and duplicate ones. We will now collect the information for all the associated and linked bugs and store this information in a data frame. After this, we will be looking into the analysis of various metadata fields associated to the bugs. Starting with priority. Priority is a field that is used to classify the bugs according to the priority. We see, according to this graph, most of the fields were unspecified. However, most of them were classified by high, medium, low, or urgent. Blocks allows us to find out if a bug is blocking other Bugzilla tickets as well. Last change time allows us to see when was the last time a bug was updated. Keywords allows us to plot a word cloud and see which are the most frequent words being used across the Bugzilla tickets. Whiteboard allows the engineer working on the ticket to write a free form of text, adding short notes and tags to the bug. Description, it contains a description for each Bugzilla ticket. Resolution are labels that allows the engineers to classify the tickets. CF doc types contains the information about if we need more documents or a release note and so on and so forth. Operating systems is various operating systems that are being affected by the bug. Target release contains various target release and we have plotted histograms accordingly. And then there's status if the ticket is closed, new, verified, assigned, and so on and so forth. External bugs allows us to see if there are any external bugs associated to the bug that we are trying to trace. Platform field indicates the hardware platform the bug was observed on. Severity, by looking at this graph, we could see that there's a bug distribution across different bug severities from high, medium, urgent, low, and unspecified. We can see the bug distribution across the various software versions as well. We can categorize the bugs into products and components, and we can see the distribution across various different components. We can also find out the product field, which indicates the software products that are being affected by the bug. We see most of them are being classified into OpenShift container platform. Summary would contain the textual summary of what was happening with the bug, what was being affected, and is open is precisely if the Bugzilla ticket is open or not. Then there were various metadata fields associated to the contact for a person responsible for fixing the bug, person who created the bug, a person who is responsible for fixing or updating the bug. And there were many other metadata fields that we explored, but turned out they are not very useful for us. For some of them were like just a Boolean value, or most of them looked empty to us. So we are not continuing using them in this notebook. And if you have any more analyses to perform, you can contribute to this page by clicking on this link. Thank you.